Welcome, ladies and gentlemen, to the multiple integration example 1 video instruction. My name is Mr. Joshua Davis and I am the math healer. Let's move forward with this problem. Evaluate the double integral over the given region by using the method of iteration. Now we're given the double integral over a region of the sine of y dx dy, where R is the region bounded by the giving information here in the bottom. Y is equal to 2x, y is equal to 1/2 x, and x is equal to pi. So I'll give you a few moments to pause the video and to copy this problem so that'll be a little bit easier to follow along. So please, at this moment, please pause the video and copy this information. Let's proceed to the next page. Now let's first examine the graph of this given information. Well, here's the region covered by the different values that we were given here. That's the bounded region given by the function y is equal to 2x, y is equal to x divided by 2, and the line x equals pi. So the region is bounded by these two functions and the line x equals pi. Now, if you go back and take a look from further review, we see that this problem or this double integral fits more of what's known as a type 1 integration problem, where the region is bounded by an upper function and it's bounded by a lower function. So we're going to use this information to make this integration of the problem a little bit easier. We also recognize that this function is continuous within this region. So based on that, here is what we know. Since f of x, y, is continuous in R, we can change the order of integration, and we're going to do that so that it fits within the type 1 double integral problem, where x is bounded by numbers and y is bounded by an upper and lower function. So here's what we're going to do. We're going to apply that information or that knowledge. So we have the double integral of the sine of y dx dy. Since we know that the function is continuous in this region and that y is bounded by an upper function and a lower function, we are now going to change the orders of integration, meaning instead of it being dx dy, it is now dy dx. Now, looking at the outer integral, we see that x is bounded by 0 and pi. X is greater than or equal to 0, but less than or equal to pi. The inner integration, we see here that y is bounded by the upper function of 2x, and it's bounded by the lower function of y equals x divided by 2. So this is what we have as our upper and lower integration for the inner integral. It goes from x divided by 2 up to the function 2x, and we're given sine y dy dx. So again, we were able to change the order of integration because the function is continuous within that region. Now we proceed to take the integral of the inner integral, and we see here that there are no x terms here to hold fixed and treat those as constants. So we're simply going to take the integral of the sine of y. We're going to take the integral of this with respect to y. So once again, there are no x variables here that we have to hold fixed and treat those as a constant. We're given simply the function sine of y. So we're going to take the integral of this with respect to y. So taking the integral of the sine of y with respect to y, we now have the integral from 0 to pi. Now taking the integral of the inner integral, we know that the integral of the sine of y is minus cosine of y, and y was bounded by the upper function 2x and the lower function x divided by 2. Now we apply the theorem of taking the integrals here, f of b minus f of a. So we do our substitutions. So f of b minus f of a. We now have the integral as we go from 0 to pi of minus the cosine of 2x minus the minus cosine of x divided by 2 dx. So we used that fundamental theorem, f of b minus f of a. Now, simplifying this, we now have the integral as we go from 0 to pi of minus the cosine of 2x plus the cosine of x divided by 2 dx. So we're now going to take the integral of this. So now let's prepare to take the integral of the cosine of x divided by 2 minus the cosine of 2x. And you probably noticed that I changed the orders of these two functions here. Before it was minus cosine 2x plus the cosine of x divided by 2. I just did the commutative property here and I interchanged the positions of these functions. So now we take the integral of the cosine of x divided by 2, and all this is with respect to x. So the cosine of x divided by 2 is 2 times the sine of x divided by 2. The integral of minus the cosine of 2x is minus 1/2 times the sine of 2x. And now x goes between 0 and pi. X is greater than 0 and less than or equal to pi. So this is where the bound was for the x. X was greater than or equal to 0, less than or equal to pi. Now we use our fundamental theorem, and we go f of b minus f of a. So here's what we have now. We now have 2 times the sine of pi over 2 minus 1/2 the sine of 2 pi. Now we see here that when we substitute in the lower integral here, the lower bound of that the angles become 0. So we recognize that the sine of 0 is simply 0. We also see here that the sine of 2 pi is also 0. So that goes to 0. We see here that the sine of pi over 2, that's 1. So we now have 2 times 1. So now we see here that the area that we were interested in is equal to 2. Ladies and gentlemen, once again, my name is Mr. Joshua Davis, and I am the Math Healer. If there was something of interest in this problem that you had a question about, please feel free to email me. And my email address is mathhealer@mathhealer.com. Please let me know if this problem was easy to follow and to understand, and if I did a good job of explaining it to you. Please have a very good and excellent day, and I wish you the best in all your mathematical pursuits. Thank you for joining me today.